Scientists think an asteroid known as Bennu can teach us more about the origin of life and solar system's history. NASA's OSIRIS-REx, the first U.S. mission to collect a sample from an asteroid, will deliver a sample of asteroid Bennu to Earth on September 24, 2023. In this video, we explain everything you need to know about NASA's OSIRIS-REx mission, including a brief introduction to the mission's primary goal, the reasons behind selecting Bennu from among the hundreds of thousands of known asteroids in our solar system, scientists' insights into Bennu and its relevance to the origin of life, the journey of the OSIRIS-REx spacecraft to reach Bennu, the preparations made by OSIRIS-REx for the sample collection, the methodology employed to gather a sample from Bennu, the forthcoming process of delivering this sample to Earth, and the post-sample delivery plans for the OSIRIS-REx spacecraft. What is the mission's primary goal? OSIRIS-REx stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. It is the third major planetary science mission for NASA's New Frontiers program, after New Horizons launched in 2006 and Juno launched in 2011. The primary goal of the mission is to collect a sample weighing at least 60 grams from near-Earth asteroid Bennu, and then bring the sample to Earth. It promises to be the largest amount of extraterrestrial material brought back from space since the Apollo era. The mission, developed by scientists at the University of Arizona, will give us more information about how the early solar system formed and about how life began. It will also help us better understand asteroids that could impact Earth in the future. There are hundreds of thousands of known asteroids in our solar system. Why was Bennu chosen? The first set of selection criteria was based on how close the asteroids were to Earth. The most accessible asteroids are located around 74 to 153 million miles away. Among these, the most desirable candidates are those with a circular orbit similar to Earth's and minimal tilting, as this makes it easier for spacecraft to maneuver. In 2008, this narrowed down the list of near-Earth asteroids from 7,000 to 192. Subsequently, the size of the asteroid became a significant consideration. Larger asteroids were favored, because smaller asteroids rotate at higher speeds, which can cause materials on their surface to be more easily ejected. This isn't suitable for safely collecting a sample. Therefore, the scientists leading the mission aimed for asteroids with a diameter larger than 200 meters. This further reduced the candidates from 192 to 26. The asteroid's chemical composition was the next influential factor, as the goal was to gather a sample that could provide insights into the history of our solar system and life on Earth. This refinement led to a short list of 12 asteroids with known compositions. Among these, only 5 were considered suitable for sampling due to their carbon-rich nature. This is crucial because a carbon-rich asteroid might contain organic molecules, volatile substances, and amino acids that could have played a role as precursors to life on Earth. Among the 5 contenders, Bennu was the only one that had been observed using radar. This provided not only accurate measurements of its size, dimensions, and shape, but also indicated that it had a relatively smooth surface with an ample amount of material suitable for sampling, and fewer large boulders that could hinder the sampling process. This level of detailed information was lacking for the other candidates, casting doubt on their suitability for safely obtaining a surface sample. Bennu and the origin of life. Bennu is a time capsule, taking us incredibly far into the past, about 4.5 billion years ago. The basic elements that make up Bennu and our entire solar system originated from a cosmic nursery, an immense cloud containing hydrogen, helium, and dust. Our own sun doesn't yet exist. Scientists believe that a nearby hot star burned up its fuel and destroyed itself in a colossal explosion called a supernova. The explosion destabilized our cloud, causing it to collapse. In about 100,000 years, gravity and angular momentum flattened the cloud into a swirling disk. In the center, where molecules collided most intensely, a young star began to intensify under immense pressures and temperatures. Deep within the rotating disk, tiny clumps of dust not much larger than a grain of wheat undergo rapid heating to transform into droplets of molten rock, known as chondrules. The origin of this heat remains a mystery. These chondrules became the fundamental components of the entire solar system. Guided by the forces of gravity and turbulence, these chondrules gathered together, forming larger clusters. Over time, they evolved into the initial asteroids, which eventually shaped the formation of mountains and planets. These asteroids were essentially conglomerates made up of a mixture of rock, metal, ice, and organic materials. The protostar underwent nuclear fusion and ignited, revealing our sun. But the entire solar system wasn't done forming yet. Jupiter probably started forming on the outer side, but about 500 million years after the sun ignited, scientists think Jupiter slowly moved inward. Its strong gravity caused disturbances in the asteroid belt, throwing them toward the sun. These asteroids hit the inner planets, causing impacts that reshaped and melted parts of their outer layer. Did these collisions also bring organic materials and water, which are important for life? Bennu managed to survive during this time of intense impacts. It gradually shifted its position closer to the Sun. The Sun's heat made one side warmer, effectively turning it into a weak thruster. Over millions of years, Bennu's path gradually tightened until Saturn's gravity influenced it, changing its course and sending it toward the inner solar system. This led to close encounters with Earth and Venus. Their gravitational forces might have stretched and reshaped Bennu multiple times, even turning it inside out and causing bits to break off. Bennu has survived its long journey and settled into a near-Earth orbit, bringing its secrets within our reach. Now it's ready to teach us more about the history, formation and changes in the solar system, as well as our own position in relation to the stars. What did it take to get to Bennu? It took OSIRIS-REx spacecraft 2 years and 101 days to get to Bennu. The complete voyage covered a distance over 1.2 billion miles. On September 8, 2016, OSIRIS-REx began its journey to Bennu from Cape Canaveral, Florida, aboard an Atlas V rocket. 1 hour later, OSIRIS-REx disconnected from its center upper stage rocket and moved into space. It deployed its solar panels to catch the sunlight, and after passing over Australia set off on its course to Bennu. After a year of orbiting the Sun, OSIRIS-REx briefly returned to Earth for a gravity assist in September 2017. The spacecraft came within 18,000 kilometers of Antarctica, then turned its instruments towards Earth and the Moon to capture images and data. The gravity assist altered OSIRIS-REx's trajectory by 6 degrees, aligning it with Bennu's orbital tilt and setting it on a path to intercept the asteroid. Starting in August 2018, OSIRIS-REx entered its approach phase. Using its long-range camera, OSIRIS-REx took the initial visible light snapshots of Bennu, depicting it as a solitary pixel moving among stars. Over the following months, Bennu transformed from a mere pixel into a recognizable object, with OSIRIS-REx unveiling its shape, rotation, and colors, marking a significant milestone in the mission. On December 3, 2018, OSIRIS-REx arrived at asteroid Bennu after chasing its target for over 2 years. OSIRIS-REx fired its thrusters to match Bennu's velocity and began the next phase of its asteroid operation. What did OSIRIS-REx do to prepare for the sample collection? After arriving at asteroid Bennu, OSIRIS-REx spent more than a year surveying and mapping Bennu before collecting a sample, ensuring that it can safely descend to the asteroid's surface and retrieve a sample of high science value. OSIRIS-REx wrapped Bennu in a complex web of observations, starting with a preliminary survey of its size, shape, mass, and spin. On New Year's Eve 2018, OSIRIS-REx was gently drawn into Bennu's orbit due to the asteroid's incredibly weak gravitational pull, making it the smallest world ever to be orbited by a spacecraft. In early 2019, OSIRIS-REx altered its orbit to conduct a detailed survey. By executing a series of sweeping passes, the spacecraft scrutinized various geological attributes at different latitudes and times of the day. This approach facilitated the creation of stereo images and the use of distinct landmarks for navigation purposes. During this detailed survey, OSIRIS-REx produced a global map of Bennu with a remarkable resolution of just 5 cm per pixel, an achievement surpassing even the highest resolution mapping of any planetary body, including Earth. On June 12, 2019, the spacecraft transitioned to a new orbit, positioning itself a mere 680 meters above Bennu's surface. This maneuver not only set a new record, but also established a stable orbit that would be its home for the remainder of the mission. Moving forward to September 2019, OSIRIS-REx embarked on a reconnaissance mission to evaluate 4 potential sites on Bennu for collecting samples later in the mission. These sites were considered as potential touchdown locations where the spacecraft could retrieve samples. Concluding its first year at Bennu, OSIRIS-REx resumed orbit, circling around the terminator of the asteroid, the boundary dividing daylight and darkness. This particular orbit allowed the spacecraft to remain relatively unaffected by external forces, enabling it to maintain a consistent path within the same orbital plane over time. Reconnaissance resumed in early 2020, with close flyovers of the primary sample collection site Nightingale and the backup site Osprey. In mid-April 2020, OSIRIS-REx conducted the first of 2 rehearsals prior to sample collection. It navigated to a predetermined checkpoint about 125 meters above Bennu, then descended to within 65 meters before backing away. Following this checkpoint rehearsal, OSIRIS-REx undertook one final reconnaissance pass over the Osprey site. Then the spacecraft executed a sequence of maneuvers at higher altitudes while restarting its onboard processor. This was done as part of the preparations for the second rehearsal of the sample collection event. On August 11, 2020, OSIRIS-REx left its regular orbit and embarked on a journey lasting 4 hours to Bennu's northern hemisphere, tracing its prior path. Once it reached its destination, the spacecraft initiated a checkpoint engine burn to begin its descent, and then executed a second engine burn referred to as match point to synchronize its rotation with that of Bennu. before backing away at an altitude of approximately 40 meters. How did OSIRIS-REx collect sample from Bennu? On October 20, 2020, NASA's OSIRIS-REx spacecraft collected a sample of asteroid Bennu. The event revealed surprising details about Bennu's surface and near subsurface. At approximately 11:30 a.m. Mountain Time, the spacecraft departed orbit. A few hours before, mission controllers on Earth had sent the commands for the touch-and-go sample collection maneuver, or TAG. OSIRIS-REx made its final descent to the primary sample site Nightingale. With its sample collection arm outstretched, it approached the surface of Bennu at 10 centimeters per second, the walking pace of a spider. Scientists had expected that the TAG event would have little impact on the asteroid. After a slow descent, the sampler head would briefly make contact, inject a puff of gas, and capture a handful of material. Perhaps it would also leave a subtle footprint at the sample site. But the impacts were far more dramatic than anticipated. Despite its slow touchdown, OSIRIS-REx had punched through the surface and set off an explosion of loose material. Tons of rocks and pebbles were ejected, radiating outward in a wall of debris. 1 second after contact, OSIRIS-REx released a canister of pressurized nitrogen, detonating an explosion of particles and driving material into the head of the sample collection arm. 6 seconds after contact, while it was still sinking into Bennu, OSIRIS-REx fired its thrusters to begin the back-away maneuver. The engine burn lasted for 24 seconds, continuously pushing against the spacecraft and rapidly slowing its descent. Flying debris from the thrusters and the gas release pelted the science instruments, clogging them with dust. 9 seconds after contact, when OSIRIS-REx had sunk nearly half a meter into Bennu, it reversed course and began to rise. At 16 seconds, the head of the sample collection arm re-emerged from the subsurface, as the spacecraft continued to accelerate. 30 seconds after contact, OSIRIS-REx shut off its thrusters and drifted away with its sample of Bennu. A later observation of the point of impact showed a new crater averaging 8 meters across and reaching 68 centimeters in depth. Thruster marks overlapped with this TAG crater in an X pattern, increasing its volume by as much as 40%. A ridge of ejected material that had been kicked up during sample collection and fallen back to the surface circled the crater like a campfire ring. Scientists had expected cohesion to act like a bit of glue between the rocks on Bennu, making its loose surface more solid. But the TAG event showed that Bennu's uppermost layers are nearly cohesionless, deforming under stress like a fluid. A good analogy is a ball pit. Although the plastic balls are solid, they easily slide past one another and past boisterous children, behaving like a fluid. Thanks to OSIRIS-REx, we now know that Bennu's surface is held together by microgravity, with a minute tug less than 100,000th the pull of Earth. Bennu has consistently defied scientists' expectations, as each new finding reveals another facet of this small but surprising world. 2 days after touching down on asteroid Bennu, OSIRIS-REx verified the status of the sample, using a camera called SAM-CAM. This visual inspection revealed whether any large debris was still attached to the sample head, which could pose a hazard during stowage. NASA's OSIRIS-REx mission team confirmed that the spacecraft had collected more than enough material to meet one of its main mission requirements, acquiring at least 60 grams of the asteroid's surface material. On October 28, 2020, OSIRIS-REx closed the sample return capsule, marking the end of one of the most challenging phases of the mission. After a final departure maneuver in May 2021, OSIRIS-REx began a 1.2 billion-mile journey back to Earth. How will OSIRIS-REx deliver the sample to Earth? After more than 2 years of traveling, OSIRIS-REx is set to deliver the sample on September 24, 2023. Releasing the capsule must occur within a specific and limited time window, and it needs to be launched at precisely the correct angle to reach its destination, a zone covering approximately 250 square miles in Utah's West Desert. On September 24, the spacecraft will come within approximately 63,000 miles of Earth. It will power up and release its sample return capsule at 4:42 a.m. Mountain Time. By 8:42 a.m., the capsule will streak into Earth's atmosphere at an astonishing speed of 27,000 miles per hour. This high velocity will cause it to generate intense heat, making it visible to ground-based infrared trackers. As the capsule penetrates deeper into the atmosphere, it will experience rapid deceleration, subjecting the Bennu samples to a formidable force of 32 Gs. Approximately 2 minutes after entering the atmosphere, it will slow down to a speed of 1,070 miles per hour, and deploy its drogue parachute, ensuring a stable descent. At 8:46 a.m., the capsule will enter a designated airspace, situated nearly 10 miles above the Department of Defense Utah Test and Training Range. Radar stations will lock onto its position, tracking it to within 30 feet of its intended landing site. Finally, at 8:50 a.m., the capsule will release and deploy its main parachute, this time at an altitude of 1 mile above the ground. It will gracefully complete its descent at a leisurely pace of 11 miles per hour, much like a marathon runner savoring a triumphant victory lap. The capsule will touch down gently in the desert soil at 8:55 a.m. After ground teams retrieve the capsule, the Bennu samples will be taken to NASA's Johnson Space Center in Houston, Texas. The sample canister will be opened in the Astromaterials Acquisition and Curation Facility, and the samples will be curated, distributed, and studied for decades to come. What will the OSIRIS-REx spacecraft do after delivering the sample? After completing its delivery mission, the OSIRIS-REx spacecraft will bid farewell to Earth. However, its adventure is far from over. In an audacious sequel, the renamed OSIRIS-APEX will embark on a journey into an elliptical orbit around the Sun. This daring path will involve numerous close encounters with the orbit of Venus, pushing the limits of its thermal design. Starting in 2029, OSIRIS-APEX will pursue and examine Apophis, a massive stony asteroid measuring 1,200 feet, which is on course for an exceptionally close pass by Earth. It plans to study changes in the asteroid caused by its close flyby of Earth, and use the spacecraft's gas thrusters to attempt to dislodge and study the dust and small rocks on and below Apophis' surface. We hope you enjoyed the video. Be sure to hit that like button and subscribe to our channel. See you in the next video.